All right, so today we are gonna do the PageRank and hopefully start also SVD. That's that's the last and best topic we are gonna cover. There's only like 3 classes left, if I'm counting right, and one last homework, one last project that's gonna be exactly PageRank, aka mini Google. So before I go there, we will sort of recap what we already had before about Markov matrices and stochastic processes. So I would like you to recall in your mind when we were talking about the rental cars in Denver example. Remember that? When I was like saying there's certain probability that a rental car will stay in Denver, will go outside of Denver, and we were looking for steady state distribution. So I don't want to repeat the same example again, but the PageRank is essentially the same idea. It's also like it's simulating web browsing as a stochastic process. And what we have seen on the Denver rental car example is that the way we can analyze the stochastic processes is using Markov matrices. So let me recap at least that. What are the Markov matrices? Because that's what we are gonna need in PageRank. So what is a Markov matrix? Does anybody remember that? If you do, then you can just yell at me. So it's a square matrix A with some properties, right? What were the properties? That's correct. Yeah. So I will write it like this, if you will, where I'm using the license that 1 is the vector of all ones. Okay. So it's a n-dimensional vector of all ones. So here I transpose it. So I sum all. It's funny, right? You basically are summing the rows. So elements in every column. That would be like the less ambiguous way of stating the same. And the other property I wanted that all the elements Aij are greater than 0. So all the elements are non-negative. Why is that? That's because they are probabilities in the Markov matrices, right? So this already implies that all the elements also have to be at most 1, right? Because if they are non-negative and they have to sum to 1, there is no way in the world how there could be anything higher than 1, okay? So this is how a Markov matrix is defined, and you should remember from what we had before, the Denver example, is that if you apply the Markov matrix 1 to some initial distribution, you will get like the next step of the distribution. So in the Denver example, it was like the status, the distribution of cars inside as opposed to outside Denver, okay? All right, so notice that the matrix A does not have to be symmetric. Okay, well, why it would be symmetric, right? There is no reason that the probabilities of going outside Denver and coming from outside Denver to inside Denver would have to be the same, right? So indeed, there is no reason to believe that A would have to be symmetric. So that might sort of raise some sort of red flags on your mind, right? That if the matrices are not symmetric, what can we in general expect in terms of complications? Because ultimately we want to be computing eigenvalues and eigenvectors, right? There will be the eigenvector corresponding to eigenvalue 1 will correspond to the steady state, and that's what we are interested in these stochastic processes. So what are the red flags this raises if the matrix is not symmetric? Well, one of them is that the eigenvalues might need to be complex, right? And the other one would be that there might not be enough of them, that the matrix can be what we call defective. But there is, in the case of Markov matrices, fortunately, there is a way out. Because of these additional assumptions of the matrix, you can prove 2 nice facts about the matrix. So fact number 1 says that lambda equal 1 is always an eigenvalue. So the whole statement would be, if I have a Markov matrix A, then lambda equal 1 is always an eigenvalue of A. So why is that? That's quite easy to prove. So I guess I can just prove it properly. So the proof is simple. So we know this property, right? We know that all the rows sum to 1. So 1ta equals 1t is true. Well, I can write this also as 1ta equals 1t identity, right? Because if I multiply by identity, I'm not going to change anything. But this means that 1ta minus identity equals 0, Okay, this is a 0 vector. Is this focused enough? Okay. So what that means is that the A minus I matrix must be singular, right? So that's equivalent to saying that the determinant of A minus identity is 0, okay? But that also means that lambda equals 1 is an eigenvalue of A. Okay, so that proves that indeed, just from the fact that all the rows of A sum to 1, you can immediately prove that lambda equal 1 is always an eigenvalue. Okay. So that's a special property of Markov matrices, which we'll use in the following, which we'll eventually use in the PageRank to show that it always works, essentially. Okay. There is another interesting fact specific to Markov matrices. So now we are talking, so all these facts have like an assumption that we are dealing with a Markov matrix. So in general, the remaining eigenvalues, they can be complex, right? Because it's not a symmetric matrix. So indeed, you can be dealing with complex eigenvalues. But what you can say is that for any eigenvalue, lambda, so in general it's complex, so that's why the C here. But what you can prove here is that the magnitude of lambda is at most 1. Okay, remember the magnitude of a complex number is the square root of x squared plus y squared, where the x is the real part and y is the imaginary part. You know that, I'm sure. No. So how do we prove this? I guess I'm not gonna do a complete proof at this point. I'll just give you an idea, so like proof sketch. Why? Like at least a rough sketch, I guess. So what we will be eventually interested in would be taking powers of k, right? Because if we have some initial distribution, we are interested in what is going to happen to the initial distribution after many applications of the matrix A, after many runs of the stochastic process. And the thing is, if there was an eigenvalue, so this is not like a perfect proof, but this is the main idea anyway. So if there was lambda complex such that the magnitude would be greater than 1, then that signifies that A to the power of k would grow to infinity in some sense. Because the A is non-negative here, that means that you cannot sort of hope for any cancellation. So indeed, like taking higher and higher powers applied to any initial distribution which is non-zero distribution, so that means sums to 1, that means that would eventually have to blow up to infinity, but that's not possible. That contradicts this partition of unity property, essentially. So this is the idea, basically. I guess if you wanted to, I don't want to like go like too deep into the mathematics because it doesn't make sense anyway. Because if you wanted to study stochastic processes properly, you would need to invest in it much more time. So I want to get into the PageRank, but I think that if you wanted to do it properly, you would write the eigenvectors of the matrix, and you would study how the A to k behaves, and you would realize that if there is something that has magnitude greater than 1, then this would just have to explode essentially to infinity. So that's what Markov matrices cannot do, and that's why all the magnitudes must be at most 1. That's the idea. So those are two basic facts about Markov matrices, which we're going to need in PageRank. There is still one more problem I would like to explain to you now. There is still one more problem. So what we are ultimately looking for is the eigenvector corresponding to the eigenvalue 1. Okay, this first fact, the one with the really simple proof, that this was actually a perfect proof, this was just a proof sketch. What we are looking for is the eigenvector corresponding to this eigenvalue 1, because that's the steady state distribution, right? That's because if the eigenvalue is 1, then the eigenvector basically is just requiring that AB equals V. That means applying the Markov matrix, doing step forward on the distribution doesn't do anything. So that's what the steady state means. It doesn't really change it anymore. Okay, we're looking at the rental cars in Denver. Outside of Denver, that means that applying the A keeps the system where it was. That's the steady state. That's what it converges to if I go with k to infinity. That's what we also discussed before, right? If we do limit k going to infinity, a to k u0, where u0 was some initial distribution, equals the v, where v is the eigenvector corresponding to eigenvalue 1. And that's what we will be ultimately solving for also in PageRank, okay? So what is the other potential problem? Well, the problem is if there are two, so just one more problem and then we'll be ready for PageRank. The one problem is if there are two eigenvalues lambda 1 and lambda 2, such that the magnitude of both of them is 1, okay? That's a problem because then this would not have to be true. Let me give you an example when, a simple example actually, a shockingly simple example. If the matrix A is 0, 1, 1, 0, okay? So please check it's a Markov matrix, it's non-negative, it sums to 1, so everything is cool, it totally is a Markov matrix, right? Fact number 1 guarantees that 1 is going to be an eigenvalue, right? What's going to be the second eigenvalue? Well, let's not compute it, I'll just tell you now. The one is 1 and the other eigenvalue is minus 1, okay? So all these facts are true, they hold, right? Because if I take the opposite value of this, I get something which is less than and equal than 1. In this case, it's actually equal, but that's cool, right? But the problem is that this fact required that all the other eigenvalues are strictly less than 1. So that all the other eigenvectors, when I keep multiplying them, they attenuate to 0, okay? If I have two eigenvalues which have both magnitude 1, that means that this is not going to happen. So what's going to happen? Well, if I keep doing the powers of a, so if I do a squared, what do I get? Let's see. So if I do a times, so I will get 1 here, right? If I do a times a, I'll get 0 here, 0 here, and 1 here, okay? So a squared happens to be exactly identity, okay? If I do a cubed, what do I get? Well, it's identity times a, right? So I will get back a. Okay, so do you see what's going on? If I do a to the power of 4, what do I get? Well, I certainly get back identity, right? So that's a funny type of, that's a weird type of Markov chain that the system keeps oscillating. It's like keeps flipping back and forth. Sort of like the pendulum on a clock or something like that. Yeah?
So the inverse of A is A?
In this case, yes. It's one of the funny matrices. The inverse of A is A. it's like an odd matrix, but like it is a perfectly valid Markov matrix, right? And the problem is that if we take a matrix like this, then this is not going to be true. So we are not able to compute the steady state distribution by iterating the powers of A and going to infinity. So fortunately, there is an easy fix for that. Or, yeah, there is a relatively easy fix. So how can we how can we solve this problem essentially? The solution is called the Perron-Frobenius theorem. Which says that if all of the elements are strictly positive, so here we require they are only non-negative, but if we require that they are strictly positive, then from this we can prove then the lambda 1 equals 1 is strictly largest eigenvalue. In other words, that the magnitude of lambda I, again, can be complex, but that's cool, is strictly less than 1 for I going from 2, 3, and so on up to n. You know that people always have the full set of eigenvalues, right? Maybe they will be complex, but in the case of strictly positive Markov matrix, we can guarantee that all the eigenvalues will be strictly less than 1. Okay. So again, I'm not gonna do the full proof. Even here it's even more technical. But I can give you the idea is actually fairly simple if you think about it. So why here the oscillation was possible? Basically, what would this mean in terms of like a stochastic process, right? In the terms of cars staying in Denver and coming out of Denver. Well, here it means that in every time I apply A, all the cars from outside of Denver come to Denver, and all the cars in Denver go outside, right? So that's why it keeps flipping all the time, right? So if you require this basically says at least some of them have to stay put, okay? And that's sufficient to guarantee that this, if I take the powers, if I iterate the Markov chain to an initial distribution, I will get to some steady state. I will not be stuck in this weird oscillating configuration. Yep.
So that means there can't be any zeros in the matrix.
That's correct. Yeah, there can't be any zeros. Yes, and that's exactly the same. We will play exactly the same trick in the PageRank algorithm. Maybe if we had a little more brightness in the projector. No, to make that happen, can you read it? Okay. Okay, fine. I can certainly see it very clearly. Yeah.
Does that cause problems? Like it seems like there might be situations where
you don't want it, right?
Yeah. You would want 0.
That's a very good point. Yeah, I think there are other ways around that. In particular, in PageRank, this is exactly what we want to use, and there's actually a good reason for that. So not in PageRank. In other cases, you might be right, and maybe there is some other things you may want to do. So this is probably okay. I don't know. I'm at the point of guessing right now. I don't think this is a necessary condition. I think it's only a sufficient condition. Meaning, if this is true, you can prove that, but maybe you don't really need that for this to hold, right? But yeah, I'm certainly not an expert on stochastic processes, so don't quote me on that. I'm just explaining this so I have like enough material to explain you PageRank. So, and that's exactly what we're gonna do. So let's just move there to PageRank. So as you probably know, the PageRank is essentially the original Google algorithm proposed by Larry Page and Sergey Brin. Is that the name? So both of them are now billionaires, co-founders of Google. And Google is now much more even just the search is much more complicated than this. But already the PageRank is a cute idea, and it's actually relatively simple, so you can implement it for your homework, which is cool about it. And it's exactly exploiting the Markov matrices and eigenvalues, eigenvectors of them. So web search, what is it about? So you have a keyword, you type a keyword into full text search, and the full text search has an index of all websites, right? It has a scroller, huge server which collected all the websites from all the World Wide Web, created an index, so it can quickly retrieve all the websites that contain your keyword. That's at least the simplest view of a full text search, okay? And just a single keyword you can imagine now for simplicity. Now the problem is, the problem that PageRank solves is that if you just type in a keyword like weather, Philadelphia, or something, or just one like Philadelphia or weather or Toyota or something, then the number of websites that contain this keyword is ginormous. Okay, so what a full text search needs to do is to order the results so that the most relevant ones are displayed first. And that's the problem that PageRank essentially is trying to solve for you, to rank the results, right, in a better way than rank them by how much everybody paid you, right? That's how some other search engines used to do that, and they did not go so well. That's how they make their money, but that's another story. Disregard how do they make the money, but let's just think about how to pick the most relevant websites from the web which contain your keyword. And the idea PageRank uses is essentially the idea of a stochastic process. So one way you can look at stochastic processes like these ants traveling through oriented edges of oriented graph. or like cars traveling from Denver outside Denver, right? So in the case of web, we will, so first of all, you can look at web as oriented graph, okay? So the individual nodes will be websites, and I will have a link, an edge, if there is a link from one website, cn.com, pointing to another website, okay? If I can click on a hyperlink from here and get onto another website. So the entire web is an absolutely ginormous, but it's just oriented graph, okay? It's clear that it's oriented, right? There could be an edge going backwards if I can go click back from this side and go back, but it doesn't really have to be there, right? It can be one way too. Okay. And the idea of PageRank is to assume a random surfer model. Have you heard that before? Okay, great. I wouldn't want to be explaining some things just so you tell me somebody already explained it to you before. So the idea to find which sites are most popular is to assume that I guess ideally you would model actual humans surfing on the web. But modeling an actual human would be very complicated, so we assume a very simple web surfer model, okay? And the web surfer will essentially be completely random, okay? It starts on some site at random. It has some oracle to just roll a dice and go to some random website, which is actually valid. Then it is on some website, and the website has some outgoing links, right? So imagine it opens a Chrome or Safari or something. There's a bunch of links, and imagine that the web surfer is absolutely dumb. So all he does is just picks randomly with equal probability between all of the outgoing links. Okay, so if I'm here, I can just roll a dice, right? In this case, the dice would have 1, 2, 3, 4, 5, 6 sides, right? And move to another link, which according to the random number I generated, according to what the dice told me. Okay, on another side, I do the same thing, and so on. And I assume I have a very large population of these random surfers. Okay, they have some initial distribution. Each of them starts somewhere, right? Some random starting site. And now they go ahead and browse the web. That's just what you do, like after work. If you are tired, you just like browse the web randomly. And after some time, if this is a valid Markov chain, and we will talk about how to make that a valid Markov chain, this will converge to some steady-state distribution. Okay, if you have lots of random web surfers, if they keep surfing for a while, well, the more popular websites, they will attract more surfers, simply because they have more links coming into them. Okay, if you are more popular, like lots of people know you, lots of people are pointing at you, then naturally more people will be attracted just by the fact that there is more links coming to that. And that's what PageRank uses to determine which websites are more popular and which ones they should be displayed first in your list of results. Okay, so that's the basic idea. You can notice that there are a few problems with this idea. For example, if I get here, if I discover a website which does not have any outgoing links, and I'm stuck as a random web surfer, right? So what I'm gonna do? That's one thing I could do, but we don't want to do that, because then what would happen, that all the web surfers would actually like get caught these websites, and your surfing would be done. So that would not be good. So what we are gonna do instead, if you just end at a website that has no outgoing links, then you just like roll the dice again and you go randomly to any website, just like you started with. Okay, that's a solution to that. Then there is another problem, that there can be potentially disconnected components, right? There's nobody to guarantee you that the World Wide Web would have to be one component. There could be like, potentially there could be like isolated components. So there is no way, if you are here, there is no link how you could get into another component here. And there is like this deep web or something like that, if you want to think about it that way. Or just like some isolated web, like of North Korea or something, that does not like let people outside. Okay, so this is the idea. So how we're going to turn it into Markov matrices and then finally to something we can compute. So what we are looking for is to compute the steady state distribution of random surfers, which tells us the popularity of websites. Okay. So we start with the matrix where so we basically encode the web and the links between the web. We encode the graph in the matrix. Okay, you probably know if you had some discrete mathematics that every graph you can encode as a matrix. In this case, it's particularly simple. In this case, the matrix, I can just draw it here, I guess. So it's going to be an n by n matrix, but keep in mind that here the n is absolutely ginormous. I don't know how many websites is out there, but it can be billions, probably, maybe even more, right? So the trick here is actually to be able to deal with really ginormous matrices. So anyway, what is in the matrix? You can still conceptually, at least conceptually, think about a matrix, okay? So if I have row number I and column number j, so I will have some number li, j here, and it tells me the probability that a user will move from website j to website I, okay? That's because when I will have some steady state distribution here, I will essentially be multiplying with the matrix, right? And this tells me the probability I'm on the website j. This tells me the probability I move to I, so that's why I'll get a distribution after one iteration of random surfing, essentially. Just exactly the same idea as with the rental cars in Denver, yeah?
So the sum should be 1, right? Along a column?
Correct. This matrix I'm describing here will be a Markov matrix, so I will want 1TL equals 1T, yes. So yeah, so for what I'm gonna do for a regular website, so if I have some website here, some node in the graph, for example here, okay, and if I have outgoing links to these 3 websites, for example, then I will just put 1/3, 1/3, and 1/3, okay? So equal probability of going to, so the idea is I'm at website J, and there is some I1, I2, I3, so the website J is linking to I1, I2, I3, and I have equal probability of transitioning to each of them, okay? So what I'm going to do, I'm going to create a column of the matrix L where I have 1/3 in the rows I1, I2, and I3. Okay, simple. And that's why it also sums to 1, just as you were asking, right? If I do this. Now, if I'm at a dead end, I don't want to get stuck there. Also, I need to make sure that the entire column will sum to 1, right? So if I'm at a dead end, what I'm going to do instead, I will simply put there if. So for example, if here let's call this J1 as this J2. If J2 is dead end, then I'm gonna just put there 1/n, 1/n everywhere. Okay, so I can transition anywhere. That's probably not readable, right? But this is 1/n. I can put it here. This was 1/3. This means that if I'm at a dead end, I have equal probability of picking a new website, okay? And this is a perfectly valid Markov matrix, right? Because certainly all of the elements are non-negative. Certainly all the columns sum to 1, okay? So this describes a stochastic process, just as I said, a random surfer model. So this third bullet is this augmentation for the dead ends. And this is what I basically said, so this is summarized here. So this is a perfect example of Markov matrix. So here I guess I have a summary of the Markov matrices. So again, if I have a state vector, pt, where I guess the t means like time, which is a distribution of probabilities, you could think about it if I have some population of like, I don't know, 10 million random surfers, then the pt times 10 million will tell you the approximate number of surfers at every node, at every time, okay? I initialize it with some p0, which can be anything. You can just say that they are equally distributed everywhere or randomly, that doesn't even matter. as we will see later, or you might remember from the Denver example. And this just applying the Markov matrix tells you the probability distribution after one step of random surfing. So meaning every random surfer clicks on the link and moves somewhere else. Okay. All right. Yeah, we have this property, the mt1 equals 1 of that's of course equivalent to what I was writing before, that 1tm equals 1t is just transpose the entire thing, and that's this, right? And as I said before, we know that the matrix, it's a Markov matrix. So even though not yet all the elements are just non-negative, but we already know that lambda equals 1 is going to be an eigenvalue of the matrix, okay? And the eigenvector corresponding to the eigenvalue 1, we call it v. So that's the vector with property mv equals v, right? Because the eigenvalue is just 1, so there is no lambda. That's the steady state distribution. So that's what we are looking for. That's basically our ranking of the popularity of the websites. Okay, so that's the problem we need to do. We need to solve here to solve the PageRank problem. Is to find the eigenvector of matrix M, or of the matrix of the web matrix, which corresponds to eigenvalue 1. Okay. So here comes here is how we justify in this random surfer model. We want to make sure that this assumption is satisfied, the assumption of the Perron-Frobenius theorem, that all of them are strictly greater than 0. So here is how we're going to augment this model. We're going to slightly alter the random surfer model so this assumption is satisfied. Okay, and we'll actually only make things better. Interestingly, so you're not sacrificing anything, you're actually gaining something. So one of the problems I mentioned before, one of the problems was that you might have isolated components. Okay, so you have a part of the web where there is no link going to another part. So there is no such thing. There could be isolated components, right? Which would not be good, because that means that the random surfer could not really traverse everywhere in the web. But there is an easy way to fix that. We can just slightly alter the definition of the random surfer. We can simply say that at every time the random surfer is doing its work, is clicking on the link, there will be some small probability the random surfer will not follow the links, but instead will get bored and will just go to a new random website. Okay, that's what we already do at the dead ends. Okay, we just go to a new random website. But we can just say that with a random probability, it can happen anytime, even if we are not in a dead end node. Okay? And to do this, all we need to do is to augment the graph with this matrix, or basically change the Markov matrix like this. Okay? So here the alpha is the probability that we will be following the links, and 1 minus alpha is the probability we will randomly choose a new website to go to, not following the links. I just got bored following the links. I want to do like something else. That's the idea. And actually makes sense if you think about it, right? So the 1,1t, is that clear to you? What does that mean, the 1,1t? That's just an outer product. So 1 was the matrix of 1s, right? Matrix like this. And 1 transpose is the same thing transposed. So the 1,1t is just a matrix of all 1s. It's just a funny way to write matrix of all 1s. I multiply it by 1 over n, so I again have a valid Markov matrix. I divide it by n, so if I sum all the columns, I get again 1, so that's a valid Markov matrix. And if I do a convex combination of 2 Markov matrices, I again get a Markov matrix. That's trivial to see, right? If I do 1t here, 1t here, I get 1, 1, and this gives me 1, 2. Yeah, in the terminology of Markov chains, this is called irreducible Markov chain, and this also makes sure that this will immediately make sure that the graph is fully connected. That's trivial, right? Because there is actually a link between any two websites, right? Because there's a small probability the surfer will get bored and will just transfer to a new website. And the nice thing is that this exactly corresponds to the assumption of Perron-Frobenius theorem, because this means that every element will be strictly positive, right? This is just 1 over, every element here is just 1 minus alpha divided by n. Well, that's certainly greater than 0, right? So that's great. So now we are out of the woods. And we actually only improve the model of the random surfer, right? So I think this is perfectly justified in the case of PageRank. So what do you think is the remaining problem? The problem is, so now we are almost done, right? Now we have a perfectly valid matrix. We know that the eigenvector corresponding to 1 will exist and will be unique. So we need to find it. So we find the ranking of the websites. That's also your project number 6 and the last project topic. So the first thing you would think about, that's the way we were doing it before. You just compute the matrix, feed it to MATLAB, and call Ike, or whatever you do to compute the largest eigenvector. We know what the eigenvalue already is, right? Well, that's not going to work for a matrix, for the Google matrix G, right? Because the matrix G is number of websites times number of websites. If the number of websites is 1 billion, then the matrix will have 10 to 18 elements, and there's no way you could even store that, right? Certainly not on a single computer. But there is good news. There is again a fix for that. Well, of course there is, because it actually works. The cool thing is that you, in this case, and in some other cases too, you can actually compute the eigenvector even without ever explicitly formulating the G matrix. Okay. So how we are going to find the eigenvector and the stationary distribution is power method. And this is just saying what I already said before, that we are looking for the steady state distribution. We cannot do it directly just by calling an eigenvector routine. But what we can do instead, is pick some initial distribution, U0, for example, all ones, actually not all ones, like 1 over n and the vector 1, okay? Because we want that to be a distribution. We want that to sum to 1. So not completely arbitrary, but has to be normalized. And then we just keep multiplying by the matrix G, okay? So GU0, let's call this U1. Then we do G squared U0, we can call this U2, G cubed U0, this will be U3, and so on, okay? And the nice thing is that as we go to infinity with this sequence of UKs, we will converge to the eigenvector corresponding to eigenvalue 1. And that's because the magnitudes of the remaining eigenvalues are strictly less than 1. So they will exponentially decay to 0. Okay? I think we discussed this when we had the Denver example. It's not very difficult to show anyway. Now you might be thinking, well, how does this help me if I can store the matrix G? Well, the cool thing is that the G matrix, to multiply a vector with a matrix, you don't have to have the matrix in memory and be calling a matrix vector multiplication routine. What you can be doing instead is just applying the matrix. So you basically, what you can do is have a function which says apply G. It's a function which you pass a parameter x. It's a vector x, and the function does something and then return gx. Okay. So this is a trick that's used a lot in iterative methods, that you don't often need to explicitly have the matrix stored anywhere, as long as you have a function that can compute the matrix vector multiplication for any vector. Okay, this is actually a pretty cool trick. It's used in like advanced multi-grid methods and so on, not just in the power method. So basically, the matrix G is procedural, if you will. Of course, if you have a function like this, you can easily recover what the matrix is, right? How would you recover it? If I give you a function to compute gx for any vector x, how would you recover the matrix if you wanted to recover it explicitly? Recover every element of the matrix. Yes, you would just pass it the standard basis vectors, right? And what this applied G would give you would be, it would give you the individual columns of the matrix.
Also, so you compute G every time you want to.
Well, you don't compute G, you compute Gx for any given x. Okay? The point is that I don't need to know G. I only need to know what G does on a given vector. Okay? So basically, in another way you can look at it is having G would be like too much of a luxury because you don't really need the entire matrix. You just need to know what the matrix does on some input vectors. If you look at the matrix as a transformation, as a linear transformation, then it's completely obvious, right? You just need to be able to compute what the linear transformation does to your vector. Yeah?
But what happens like in the function to make it faster? Like
I'll get to that in a second. I will show it's actually right here. So the final Google matrix G looks like this, okay. So this is after the fix that the random surfer can get bored, okay. That's the probability of going randomly to somewhere else. And this is the product Gx, okay. So let's take a look what that means. Oh, and the matrix L we can further decompose into H, which is the matrix of the links in the original web, and this 180x, that's just the fix of the dead ends, okay. So the A would, okay, let me write it here to make it clear. So or I guess the A transpose would be an indicator of the dead ends, okay. So it would be mostly zeros, and I would have ones corresponding to the dead ends. Dead end nodes. So nodes that don't have any outgoing link in the H matrix. So this is the fix for that. Okay. This is basically, this is like writing it down really explicitly, because in the project what I will give you is the matrix H, and you will have to augment it with the fix for the dead ends and the fix for the random board surfer. And here is what you were asking about, essentially. How do we efficiently compute the Gx for any given x, okay, without ever computing the G explicitly? Well, now we know the components of x. So the H will be a sparse matrix, so you just deal with that. That's the data, okay. So that you do need to store somewhere. It better be stored as a sparse matrix, right? Because that the H matrix will be very sparse. I guess the only problem with the G was that this part was not sparse, right? This was a completely dense part, the 1,1T, okay? And here is how we can easily circumvent it. If you have to compute 1A transpose, so again, what is 1A transpose? So 1 is a vector of all ones, okay? And A transpose is, let's just say it's any, it's A1, A2, up to AN, okay? So that's an outer product, right? So this is certainly an n by n matrix. So if I'm computing 1A transpose X, I would normally just compute 1A transpose and do a matrix vector product, right? But because of associativity, I can just do this. I can just say it's ATX, okay? That's what I've done here already for you. And then computing ATX, that's just an inner product, right? So I never have to explicitly form this 1AT matrix. I can just compute it as two dot products. Do you see how that's much more efficient? If you needed to compute the matrix explicitly, you would need n squared memory. Here you need only linear memory, right? To only store the A, X, and the ones. So that's how you efficiently compute the action of G on any vector X without ever explicitly formulating the G. Okay? This trick is used a lot in like iterative methods. Yeah, so that's basically what I said, summarized. Slim. This HX, that's the sparse matrix multiplication, and these inner products, those are the fixes for the dead ends, and the fix to make sure all of them are positive, and also to make sure that the power method is always going to converge. Yeah?
How do I get the value for alpha?
Sorry?
Alpha, the probability alpha.
How to set that? Or?
How do I find a number? Like I know L, the probability L,
Mm-hmm.
I know, but alpha, how do I get?
That's a great question. That's basically a parameter, right? So you have to set it to something. I think in the project, I think I gave you some value to use. I don't remember. I mean, this is like a tweaking parameter, right? It's you can try multiple ones and see what happens. That's like as a good answer as it gets, I guess. I guess if you wanted to be like scientific about it, you would like try to think like what is the most reasonable random surfer model and like try to derive the probability of going randomly to some other side based on some other grounds, right? Like what's the probability if a person gets bored? You could do some like cognitive science around it or something. All right. So that was PageRank. So it's really not that difficult. It's just very fun type application. So that's what you're gonna do. I need to clean up the project a little bit, and I'll submit it tomorrow, I think. Okay. So unless you have any more questions to this, we will switch to SVD. Yep.
So it means if we use this, there will be more computation, but save a lot more memory. Okay.
Actually, there will be even less computation, right?
Less.
Here would actually also have to read it, so the computation will be also n squared. Here it's just like 2n, which is n, right? So it's saving on both counts. Basically, like doing it this way would be another way of saying this. Doing it this way, explicitly forming the matrix, would be incredibly stupid. Okay. So the last and best topic is a single value decomposition. So I guess we will get started today. I'll at least give you the key ideas, and then we will fully prove it and develop it next time. I think I will do at least some proofs better. So I guess one way you can approach SVD is if you ask yourself the question how to generalize eigendecomposition or eigenvectors. Okay. And we would also like to be able to support rectangular matrices, so matrices M by N. Okay. So how could we generalize the idea of eigenvectors? So remember, eigenvectors, well, AV equals lambda V, right? And even for square matrices, they didn't always have to exist, not all of them, right? There could be these defective matrices which wouldn't really have a linearly independent set, full set of eigenvectors and so on. Sometimes you have to go to complex numbers. And you cannot even think about supporting rectangular matrices, right? Because this V has the same dimension here, right? So if we have a rectangular matrix, then this doesn't even make sense. Even type check will fail on this, right? Because if this is an m by n matrix, this is n by 1 vector, then you will get m by 1 vector back, so that there's no way that could be equal to n by 1 vector, right? So that's, we need to come up with something else if we want to generalize it to m by n, and the answer is singular values and singular vectors. So it's a similar idea. Instead of eigenvalues, we will have singular values. Instead of eigenvectors, we will have singular vectors. Okay. Now we need to be a little more refined here, a little more careful here, because instead of just one eigenvector, we will actually deal with two types of single vectors, left and right. So let me write the defining. The defining properties are similar to eigenvalues and eigenvectors. So if I have a singular vector b, then I want this to be true. So let me first write it and then I will explain it. A transpose ui equals sigma I pi, okay? So here the vi is a right singular vector. Ui is a left singular vector. And the sigma I is a singular value. So the first thing to remember, I guess, is that the singular vectors come in pairs. There's a left and right one. So basically, I guess you can think about it as splitting the concept of eigenvector into two pieces, into like a left one and right one. And that's what you need to do because the matrix is not square in general anymore. Okay? And here from these properties that needs to be satisfied, so we can talk about single values and single vectors, they sort of can remind you of eigenvalues and eigenvectors, right? The only funny thing is that here the right singular vector gets mapped through the matrix A onto the left singular vector. So the V is the right singular vector, U is the left singular vector, and the sigma is the singular value, okay? So you can see similar sort of idea as with the eigenvectors and eigenvalues, we just have to refine it. Okay, and here the A transpose, it maps the left one onto the right one using the same singular value. Okay, so another way of writing this, if I transpose everything, I can write the second property as UIT transpose A equals, this stays the same except that I transpose the VI. Okay, and that's why the U is called the left singular vector, because it essentially multiplies the original matrix A from the left, and the V multiplies the matrix from the right. Okay, that's why we need to split it in two, because the matrix is rectangular, so there's no way one vector would work from both sides, right? So that's why we need to have two. That's one way you can think about it. The cool thing is that everything is real here. The UI is RM, and 0 is also forbidden, just like in the case of eigenvectors, when I was always saying that 0 is not a valid eigenvector, that's forbidden. The same thing is true for singular vectors. So they are like this, and it turns out that the singular values, not only they are real, so let me put it here, that they are real, but they are also non-negative, or you can always choose them to be non-negative. Okay, so there you can immediately see an advantage compared to eigen decomposition, because here, if my original matrix is real, and that's the case we are mostly interested in, you never have to go to complex numbers, as we had to in with eigenvalues and eigenvectors. Okay, the single values and the single vectors, they always are real for a real matrix. You can also do a SVD of a complex matrix, but let's not go there in this class anyway. So that's basically one way how you can define single values and single vectors, and one way you can look at them as a generalization of eigenvalues and eigenvectors to rectangular matrices. Then there are other ways how you can arrive at the same concept, which I will discuss later. So the UI, of course, needs to be from m-dimensional Euclidean space, right? Because that's just so that the types match, right? VI must be n-dimensional, so I can multiply. A is, so I guess I should put it here. A is an m by n dimensional matrix, okay? Now you can notice from these defining properties of single values and singular vectors, I can say even stronger statement about the U's and the V's. That's actually important because single value decomposition is intimately related to the four fundamental subspaces theorem, which we had a couple weeks ago, maybe more months. Wow, it goes very fast. The fourth fundamental subspace, a single value decomposition essentially is providing an orthonormal basis for the four fundamental subspaces. That's what I would like to get to. Okay. So the first thing we need to realize is that I can say more about the singular vectors. So the left singular vectors UI, not only they are from Rm, but they are also from the column span of A. Okay. That's because you can see it from here, right? The UI is certainly a linear combination of columns of A if this equality is true, right? Similarly, I can say that the VI is a member of the row span of A. Oops, sorry. The row span of A means the column span of A transpose, right? We have been through that because transpose exchanges the role of columns and rows. Let me write it nicely again. CA transpose. Okay. Again, that's obvious from here, right? Or here. Here I'm taking the columns of AT and their linear combination creates the right singular vector V. Okay. By the way, I put there the I here because I start with I equal 1 and I find the first singular value and the two singular vectors, the left and right singular vectors. Then I can move on to I equal 2 and find another different triple of single value and the left and right singular vectors. And I can keep going until when, do you think? How many single values and single vectors I can find? And let's say if it's non-zero sigma. So the sigma is always greater or equal than 0. And particularly interesting will be the single values and the singular vectors corresponding to single values which are strictly greater than 0. How many of them do you think I will be able to find for an arbitrary rectangular matrix A? Just like you can just guess.
Lesser m.
That's correct. That would be true even if I allowed the 0 single values. The nice thing is that, I guess it will make more sense later, but it's sort of cool. It will be exactly the rank of A. And I guess that's why it's called single values and singular vectors, because it essentially lets you detect the singularity of A. We will get there. So let's start by recapitulating the column spans and row spans, because you might have already forgotten what they were. So I just pulled up the old slide. So the column span is the linear subspace which you get by taking linear combinations of all the columns of matrix A for a rectangular matrix A. Okay. I want to recapitulate the four fundamental subspaces thing because SVD essentially just refines that idea. And we showed, or maybe we didn't show because it was so simple, that the column span indeed is a subspace. Okay. Now the null space was a similar idea, but in this case we were looking at a subspace of vectors which the matrix A maps to 0. Okay, remember that? That was the null space. We also had the row span. The row span is nothing special. That's just the column span of AT. So in other words, it's a linear combination, the subspace generated by linear combinations of all rows of A. Okay. And the last thing we had is the left null space. So that's also the null space of AT, and that's simply the space of all vectors A such that ATY maps them to 0 for any A from Rm. And that's of course equivalent, or let me put it like this, YTA equals 0. Okay? And all these four fundamental subspaces are nicely tied together in this diagram. So let me show it again here. So if I have a matrix A, which is an M by N matrix, so the matrix A maps from N-dimensional space to M-dimensional space, right? It takes an N vector, and maps it into an n vector. And the other way goes the matrix AT. It takes an m vector and returns me an n-dimensional vector. Okay? And we said that for absolutely any rectangular matrix, you can form this picture, which is interesting. So here, this is basically orthogonal decomposition of R to n. It's there are two. The R to n splits into two orthogonal subspaces. That's the row space of A and the null space of A. And similarly, Rm splits into these two, into the column space of A and the left null space of A. Okay? And if you remember how this worked, the idea was that if I took any non-zero vector from the row space, it got mapped to a non-zero vector in the column space. Okay? And similarly back, if I took a non-zero vector in the column space, it got mapped into a non-zero vector in the row space. If I took any vector in the null space of A, it gets mapped to 0. So all the vectors here get mapped to 0, this one. And similarly, all the vectors in the left null space get mapped to 0 here. Okay? So that was the idea. Just recap. We had this before. I'm just refreshing your and my memory. Okay, and basically I guess the most important message from this picture was that in any m by n matrix, there is R by R invertible submatrix hiding in there, or R by R invertible component in there, where R is the rank of the matrix. Okay, so this also gives you the dimensions of the row spaces. I guess I have it summarized on this slide. So both the column span and the row span, they have dimension R. That's the rank of the matrix. And the null spaces, they essentially complement it to the full dimension of the spaces where the matrix operates on. And the most important, I guess, the most important part of the matrix A is the invertible mapping, which goes to R-dimensional subspace of Rn to an R-dimensional subspace of Rm. And the AT would be going the other way around. Okay? So, let's take a look at the one way how you can sort of develop SVD. So we start with this defining property of eigenvectors and eigenvalues. Okay, that's what I said before, at least one side of it. And let's try to write this in matrix form. Okay, so if A is an m by n matrix, so let's just put it here. So A is an m by n matrix. So I can just, and this works for I going from 1 to the rank. Okay, let's say we somehow found the single values and the corresponding left and right singular vectors. How to find them? This is what I will explain the next lecture, but let's just assume that somebody gave us to them, and let's see what we can do about it. Okay, so one thing I can do, I can just stack them in a matrix. Okay, and I can call this matrix, let's call it V tilde, this entire matrix, and it's going to be an n by R matrix. Okay. And if I basically write all these equations at once using matrix equality, so here I take all the left singular vectors and stack them into a matrix which I'm gonna call U tilde. This whole matrix is U tilde, and it's an m by R matrix. And these sigmas I can put here into a square matrix of the singular values. Okay, so this is an R by R matrix, and I can call this matrix sigma tilde. Okay, so maybe let me write it in a more clean way as A V tilde equals U tilde sigma tilde. Okay, that's the same thing as this for I going from 1 to R. That's a matrix version of all these equalities. Okay, similar to what we are doing when we are doing eigenvalue decomposition. Now the cool thing is, and again I will show this properly next time, is that we can find these right single vectors in such a way that they are orthonormal. Okay, and furthermore, well, because there is R of them, and because, as I said before, the right singular vectors are in the row space of A, they will actually form a basis of the row space of A. Okay. Similarly, the left singular vectors can be also chosen to be orthonormal, and they will be the basis of the column space of A. Okay. So the best way to do this. Yeah, I think I can do this. So, so far, basically, this is the way to isolate the R by R invertible component of A. Basically, that's what the sigma tilde is. Yeah.
But shouldn't U and R U and sigma be different? Should they swap places? Because
Yeah, you wanna see like the U sigma V, right? Or
because like on the left side, sigma is sigma I U I. But
Yeah.
Why wouldn't we expand it to a?
that's correct, no?
Okay, yeah.
I mean, so this multiplication means multiply the first column by sigma 1, the second column by sigma 2, and so on, the last column by sigma R, right? So that's exactly equivalent to this. Okay. Okay, so that's basically so this sigma. Is that clear? So the sigma tilde is basically the invertible component of the matrix A. Okay. So the next thing I want to do, I want to build in the null spaces. Okay. So the V tilde, so or the V. Oh, let me write it like this. So let me do this properly. So we want to VR are an orthonormal basis of the row space. Similarly, the U1 vectors will be orthonormal basis of the column span. Got that right. And what about the null spaces? So if I take the null space of A, it has dimension n minus r, right? And the null space is a subspace of R to n. And we know that we can find vectors Vr plus 1 up to Vn, also n-dimensional of course, such that the entire sequence, if I start from V1 and go all the way down to Vn, are orthonormal. Okay. And for the left null space, that's a subspace of Rm, of course. It has a dimension m minus r. And we can complement them, this is sometimes called complement, to a basis of the entire subspace, of the entire space, with vectors ur plus 1 up to um. And that's from the m-dimensional subspace. And again, all of them going from these guys up to the last one, up to the are again orthonormal. Okay, so if I write the full picture here, what I started with was the matrix A. Let's assume it's this dimension. If it had the if it was the tall and skinny matrix, the picture would be similar. So here is my V tilde matrix. Okay, so let's say that this is my V tilde. That's what I had here. Those are the right singular vectors corresponding to non-zero singular values. And that's an n by r matrix. And here I complement it with these remaining guys, so I get a basis of the entire R2n space. Okay, so this is an n by n minus r complement. Okay, So altogether, I got an n by n matrix, which I can call V. Okay. And on the other side, I have, this is what was my original U tilde. So this must be the same length as this, and this must be the same size as this. I'm trying to make the picture correct. This is m by r. And here it's complemented with these remaining guys from r plus 1 to um. That's the orthonormal basis of the left null space. So that's the m by m minus r component. Altogether, it will be a nice square matrix, m by m matrix, which I can call U. Okay. And here I just need to complement the sigma tilde matrix. So here this is an r by r submatrix. Here this is my sigma tilde. That's this one. And here everywhere else are just zeros. Okay. So this is an m by n matrix. And I can call this sigma. And here I have the orthonormal basis for all of the four fundamental subspaces. Okay. Here the columns here are the orthonormal basis of the row space. The columns here are orthonormal basis of the null space. Here the columns of U tilde are orthonormal basis of the column space. And the complement here are the left null space orthonormal basis vectors. Okay. So the beautiful thing here is that both V and U are now square and orthonormal. Okay. And the one cool thing about square orthonormal matrices is that the inverse is just transposition. Okay. So here we had matrices which have only orthonormal columns. Okay. And you also had just orthonormal columns. Here, if it's a square matrix with orthonormal columns, we know that immediately implies that also the rows are orthonormal. And that implies that I can define the inverse. I mean, it's square, so I can only talk about inverse of a square matrix. And it's equivalent to the transpose. Okay. So if I write this in the matrix language, if this is A, V equals U sigma, then what I can do, I can multiply both sides of this equation with V transpose. And if I do that, then VV transpose reduces to identity, right? Oh, let's do that. U sigma VT. This is going to be identity because V transpose is V inverse. So VV inverse is identity. So, and this is the, I guess, the famous form of SVD factorization, single value decomposition, where I started with an arbitrary m by n matrix. I get an m by m orthonormal matrix U. I get an m by n matrix of single values, which is diagonal, and all the single values, all the elements on the main diagonal are greater or equal than 0. There is exactly r of them which is strictly greater than 0, and the remaining elements are completely zeros. And the V is an n by n orthonormal matrix. Okay. So this is what the SVD is, and this is how you can interpret the contents of the matrices U and V. Okay. So I guess the point of this lecture is just to explain what the SVD is, and next time I will show you why does it always exist and how to compute it. Okay. But so to try to in your mind try to connect it with this picture. Because the basis for all the four fundamental subspaces, they are written right here. Okay, so if you call SVD in MATLAB, then you immediately get orthonormal. That's a luxury. Orthonormal basis for all the four fundamental subspaces. And here the matrix, basically the only payload. This is only change of basis. Okay, this is only rotation or reflection. There is a way to deal with the reflection. We will discuss that later. But this, you can interpret the V and U as just a change of coordinates, right? Just going into a different orthonormal coordinate frame. So basically, all the matrix A really does is this, the sigma part. Okay, so that's I guess the most informative way to, or how do I put it? That's the, I guess, the best way to understand what a matrix really does. It does one coordinate transformation, then it does uniform scaling in all of these axes. So the single values are essentially the individual scaling coefficients, and then it does another coordinate transformation. That's basically what SVD means, right? You could also look at it from a different perspective. You could also say that UTAV equals sigma, right? So basically, these are matrices. If you cannot diagonalize it, well, you can't because it's a rectangular matrix, right? We only talked about diagonalization for square matrices. But here you can instead find two matrices U and V, so you can find a diagonal rectangular matrix. And this is incredibly useful. This essentially makes lots of linear algebra trivial if you have the SVD, which is a big if. Because computing SVD for the Google matrix, you can pretty much forget about it because the U and V matrices are going to be dense. Okay, so it's like the SVD is the big sledgehammer of linear algebra, and we will talk more about it and why is it so important in the next two lectures. Okay? Any questions? All right, so I'll let you go. We'll meet again on Wednesday.